So, welcome, and I hope today you'll have a fun and exciting learning session. So, we've been using waves in more ways that we can think of. For example, we've been using it as a tool for communication using radio waves. Also, we've been heating our food using microwaves, and we've been tracking anything or anyone using GPS in our cell phones. So, today, this will be about waves. We have classification of waves, properties of waves, and of course, describing waves using math. So, what are waves? So, the most simple definition of wave is that these are disturbances that carry energy. So in the left, we have a slinky, and in the right, we have a very big wave, and that's what we call as tsunami. So all waves carry energy, and these are all disturbances. So at least once in your life, you must have played the slinky before in stairs. Okay. So the initial energy, or let's say the initial motion that you've transferred to the slinky, travels back and forth to this kind of spring, and it moves on its own, right? And sometimes waves can also be very destructive, like tsunamis. It carries a very high amount of energy and it destroys everything in its path. So we can classify waves first, either it will be longitudinal or transverse. So longitudinal waves are like this. So the most defining characteristic of a longitudinal waves is that it travels to left and right, and its speed, or let's say its velocity, travels from left to right, and also its particles. And it also has this characteristic of compression and decompression, or what we call as rarefaction. So compression, from the word itself, some parts are compressed, some parts are less compressed, and so on and so forth. So just like a slinky, it compresses and then decompresses, and the pattern continues. So one wavelength is the length of from one compression to another compression, or from one rarefaction or to another rarefaction. Then we have these transverse waves. These are the waves that we usually see in math. And this is also the wave that we see in ripples or in water, just like waves, water waves, ocean waves, and so on. And of course, strings of a guitar or instruments. So we have this labeled as their parts, and the maximum point, that's what we call as crest here and here. And the minimum point, that's what we call as trough. And the length of these, the amplitude, or that is the length from crest to its resting point, or from the trough to its resting point. Another way of classifying waves is be labeling it as mechanical or electromagnetic. So mechanical waves are waves that need a medium to propagate. For example, sound waves. Sound waves needs the medium to propagate, let's say solid, liquid, and gas. So there are no sound waves in outer space because outer space is empty and there is no medium to travel. While electromagnetic waves are waves that doesn't need a medium to travel. So they can travel anywhere. They can travel in air, in solid, liquid, or gas, and they can even travel in the empty space. So here are the examples of electromagnetic waves. So to the right, from left to right, that's arranged in increasing energy or increasing in frequency. While from the left to right or to the left, that is arranged in increasing wavelength. So first example, let's start from the left, is the radio wave. That's what we use in listening, using our radios, and sometimes also these are also the waves, the kind of waves that the signals that is perceived in our cell phones. Microwaves, well, this one is amazing because this is where we cook or heat our food. And this is, by the way, discovered by James Clerk Maxwell. Well, he is a very famous scientist. And we have infrared. This lets us see different heat signatures. We usually see this in airports. Visible light, of course, we know this. This is what enables us to see. Ultraviolet rays, this can be very harmful. And this is responsible for sunburns. X-rays, this is the kind of wave that lets us see through our bones. And we have gamma rays, which are very energetic and very harmful, but can also be used to treat cancer. So, properties of waves. Once again, um, we have these crests, we have these troughs, and the amplitude, which will be labeled as capital letter A. That's the length from the resting point to the crest, or from the resting point to the trough. So here we describe waves using math or using numbers. First, frequency. That's small letter f. The frequency is this is the number of waves produced per unit of time, and its standard unit is hertz. And 1 hertz is equivalent to 1 wave per second. So one cycle, going back to this, one cycle constitutes from crest to crest here, from starting from here, going here, and then here. That's one cycle. The next we have period that's labeled capital letter T. This is the time taken for one complete cycle. So the standard unit is usually in seconds because it's the time taken. And its formula is T equals 1 over F. This is the inverse of the frequency. Oh, and if you want to use the triangle method, you can write it as like this. T equals 1 over F. Then we have velocity. This is the distance or displacement traveled by a wave per unit of time. So I might interchange distance and displacement and even velocity and speed here since we'll be defining our waves as moving from left to right all the time. So the formulas that we will be using is V equals lambda F and V equals lambda over the period or capital letter T, where lambda is the wavelength. This is the length of the wave. And using the triangle method, we can write these two formulas here. The first one is like this. V is at the top, and we have lambda F. The second one is V to the left, and then lambda over T. So we have an example. What is a wavelength of a transverse wave that has a frequency of 10 hertz and a speed of 30 meters per second? So, we have different ways in solving this, but I prefer to solve this, or I prefer to start with given, or prefer to start with writing all the givens. So, all the givens, we have the frequency, 10 hertz, and we have the speed or velocity. Once again, I might interchange speed and velocity in discussing or giving examples in waves. 30 meters per second. So V or speed will be interchangeable in waves discussion. Once again, okay? Then after writing all the givens, I will write something that is what we are or the parameter that what we'll be looking for. So we're looking for or we're finding the wavelength. What is the wavelength? Okay. And after this, I will look at these all of these terms, all of these parameters. We have F, we have V, and we have lambda. And we'll look at our formulas. Which formula should we use that has F, that has V, and that has lambda? So let's go back to the formulas. Let's try this. That has V, that has lambda, that has F. No, not this one. But V, lambda, yes, this one. We'll be using this one and this one as well. So we'll be using V equals lambda F and this V equals lambda F. Specifically, we are looking for the wavelength. So we have to, cover wavelength and equal sign. That's V over F here. This will be the formula that will help us solve this problem. Then just substitute. Our V is 30 meters per second. Our F is 10 hertz. 30 divided by 10 is 3. And the unit is meters because our velocity here, speed, is in meters per second. So more examples will be given during our synchronous class, and I hope you learned more on this. I hope you enjoyed learning waves. So for now, goodbye and thank you. You have a great day.